So today we're going to cover the second half of EMR, just in some review in preparation for that unit exam. So EMR Part 2, that's the name of the game today. So it's pretty much the same thing as last class, just different content, of course. We're focusing on EMR Part 2. Once again, it's going to be one of those you try, I go over kind of days. Remember that this half of the EMR unit covered wave nature of light, which includes Young's double-slit experiment. Polarization of light, we're not going to do any questions on that today. It was just basically understanding what polarization is. Quanta of light, which is talking about photons and their properties. The photoelectric effect, which of course is where basically when light of a certain wavelength or frequency strikes a certain type of photoelectric surface, electrons can be released. And then last but not least, the Compton effect, which talks about how a photon can scatter an electron when they collide. Anyway, moving on, let's get started. It's going to be one of those you try, I go over kind of days, so be prepared. Here we go. Question 1, a student measuring the wavelength of light emitted by a krypton gas sample directs the light through two slits separated by 0.264 millimeters. An interference pattern is created on a screen 3 meters from the slits, and the distance between the second bright fringe and the central maximum is measured to be 1.18 centimeters. What is the frequency of the light emitted by the krypton gas sample? Pause the video here, we'll go over in a second. Okay, so the key thing here is making a very effective data bank, and yes, I understand this is quite challenging, of course. There's a lot of variables involved with these Young double-slit experiment questions. I'm just going to walk through it bit by bit. This is the distance between the two slits. Now, the slits occur in something called a diffraction grating. I'll write that down, a diffraction grating. And how I always remember this is, of course, diffraction grating starts with the letter D. So the distance between the slits in the diffraction grating is going to be D. So D is equal to 0.264 millimeters, but that's milli, so I'm going to turn it to meters. That's 0.264 times 10 to the negative 3, because that's what milli means, meters. Next one, the interference pattern is created on a screen this far away. Well, I just always remember that as being L. I'm not really sure why I've always found that one so easy. L is the distance from one screen to the other. It's the length between the screens. I don't know. I just always found that one a little easier to understand. The distance between the second bright fringe. Ooh, there we go. Second bright fringe. That means N is going to be 2 because this is the second one. Is measured to be 1.18 centimeters. Now, of course, the distance from the central maximum to whatever antinode you're looking at, that can change depending on a lot of things. Like that's the thing that really changes a lot. And since it changes a lot, I think it's very appropriate that it's given the letter X. So X is going to be 1.18 centimeters. I'll change that into meters. That one, I don't have to do it quite as challenging as that. I can just make it 0.0118 meters. Yeah, there we go. All right, so the question's asking, what is the frequency of the light? So frequency is F. But you might notice in your formulas, F doesn't show up directly, but remember F with light is directly connected to the wavelength lambda. So I'll really say we're looking for lambda first, and then we can find our frequency. Now, what's important is, as you can tell by these variables, it's kind of setting up the formula. Lambda is equal to XD over NL. That's called the small angle approximation. You can't use that unless you know that your angle is less than 10 degrees. So I'll do this proper. Let's actually draw our two screens here. And let's make sure that that angle is actually less than 10 degrees so that we can use this formula. Well, I'm not going to draw all my little slits here or anything, but I can draw that this is the distance between the two, so that's 3.0 meters. There's going to be some angle forming. That's the angle we're looking for. And this, of course, is the distance from your central maximum to your second bright fringe, so that's your 0.0118. So to find this lambda, or sorry, to find this theta, this angle right here, we just have to use a little bit of right triangle trigonometry. There's a right angle that forms right up here. This would be the opposite side. This would be the adjacent side. So therefore, we're going to use tan. So tan theta is going to equal 0.0118 divided by 3. Take the inverse tan of this, and you're actually going to find your angle is nowhere even remotely close to 10 degrees. It's actually 0.225 degrees. So it's even a lot less than 1 degree. This is a tiny, tiny angle. So very clearly, we can use our small angle approximation. So let's go through with that. Lambda, our wavelength, is going to equal X, which is 0.0118, times by D, which is 0.264 times 10 to the negative 3, divided by N, which is 2, times by L, which is 3.0. You can throw this in your calculator all in one swift go. And what I got was 5.192 times 10 to the negative 8. And that, of course, is in meters because it's a wavelength. Now that's not what we're looking for though. We're looking for our frequency, but remember by the universal wave equation, we know V is equal to the frequency times by the wavelength. That is also on your formula sheet. We can rearrange this just by dividing by lambda on both sides. So we can say that frequency is V divided by lambda. V in this case, of course, is the speed of light, and that is known. So we can say F is equal to 3.0 times 10 to the 8, yeah, speed of light, divided by lambda, which is 5.192 times 10 to the negative 8. This is going to give us a final answer to just 2 sig digs, because notice this here was just 2 sig digs. Our frequency is therefore equal to 5.8 times 10 to the 15, and the units on that, of course, are hertz. So again, with the Young's double slit questions, the hardest part in most people's opinion, I think, is just getting all these variables together. With the whole online learning system, I have no issue with you guys writing down like a little cheat sheet saying what is what. But if you had to remember this, or if you really, really wanted to remember it, again, understanding that D is the diffraction grating and X is the distance from the central maximum to your antinode that you're interested in, that's another way of doing it, but whatever. Anyway, moving on. Question 2, a blue laser emits photons with a wavelength of 470 nanometers. If this laser emits 2.50 times 10 to the 22 photons per minute, what is the power of this laser? Pause the video here, give this one a try. So there's a couple different ways you could go about this one. I kind of debated between the two. Like really it's the same general pattern, but it just depends on when you're going to divide. Keep in mind this is photons per minute, right? You can save that whole idea of a minute to the very end. Personally, that just made me uncomfortable. I'd rather just deal with it and get it down to seconds for now, because remember, a minute is not the standard unit in physics, seconds are. If this is how many photons come out of here per minute, we just divide this by 60 to find how many photons come out of this per second. The answer to that would be 4.1666 repeating times 10 to the 20 photons per second, right? Now, why is that useful? Well, remember, we're trying to find the power here. Power is equal to work over time. Time, we can just consider 1 second now that I've already dealt with it, but we need to find the work. Work, however, is just a change in energy. So really, we can just consider energy our work in this case. Bottom line is, we need to find the energy of these photons per second. We know the wavelength, so we have a lambda. If you look on your formula sheet, you can actually see that there's 2 equations for the energy of a photon. There is E is equal to H times F, but that's not going to be super useful to us because we don't have frequency, we have the wavelength. We can find frequency, no problem, but you don't even have to do that because they've already done it for you in another equation on your formula sheet. E is equal to HC over lambda. That just finds F, just builds it right into the equation so you don't have to go around and do another step, right? So let's use this one. That's going to allow us to find E that we're going to use in place of our work to find our power. So it's going to be a big old chain here. So we're going to say it's E is equal to H. Now H, just by the way, there's 2 different H values. Oh, wait a minute. I got to back up. I almost goofed up here. My mistake, guys. This is the formula for 1 photon. We have a lot more than just 1 photon. Well, this is actually quite nice because since this is the equation for the energy of 1 photon and we have many photons, why don't we just times it by the number of photons? Yoink, we just put an N right there, right? You can put an N right here too if you wanted to, even though we're not going to use this one. Right, anyway, so we've got to multiply by our N first. Now, what I was getting at is there's 2 different values of H. There's one that's in joules and there's one that's in electron volts. Generally speaking, especially when you're dealing with power, joules is probably a better way to go. Matter of fact, it is the better way to go. I'm not even going to beat around the bush on that one. It is the better way to go. It's what you have to do because joules are the standard unit of energy. Electron volts are just nice for communicating certain things. That's about it. Anyway, I'm going to stop rambling. Let's throw these numbers in. N is 4.166. I'll just throw another 6 in there for good measure, times 10 to the 20, times by H. H in joules is that 6.63 times 10 to the negative 34. C, of course, is the speed of light, 3.0 times 10 to the 8. And then divide all of that by your wavelength, which is 470 times 10 to the negative 9. This is going to give me energy is equal to, actually a pretty nice number, 176.33 roughly, and of course that's in joules, but we don't want that, we want our power, although you're going to see something kind of funny with this in a second. Power is equal to energy over time, so it's going to equal 1.7, oh sorry, not 1.7, so used to standard or scientific notation here, 176.33 divided by our time. Now, since we divided by 60 in the first place and we found our photons per second, our time in this case is just 1. So this leads me to a final answer to 3 sig digs here of 176, and the units on power are watts. So 176 watts. If you didn't divide by 60 in the first place and you just use this number, then down here, you would have to divide by 60 because, of course, your time there had to be accounted for. So either way, though, you'd still get 176 watts as your final answer. All right, next one. Quite a long one to read, but I'll read it out to you and then I'll get you to try it. Students studying a metallic surface are shining a variable frequency radiation source on the surface. They begin to shine infrared radiation on the surface and slowly increase the radiation's energy until they detect the emission of photoelectrons once the wavelength reaches 832 nanometers. If they slowly decrease the wavelength of the incoming radiation until it becomes visible red light, 710 nanometers, what is the maximum kinetic energy of the emitted electrons? Ooh, photoelectric question. These ones are tough. Pause the video, give it a try. Okay, so there's a bit of things to take into account here. This one was actually quite a challenging one, so if you weren't able to get it, don't kick yourself too hard, but I'll show you how to go about it and make sure you understand it, and make sure you reach out to me if you don't, even when I'm done going through it. Notice right in the middle of this question here, it says they start detecting those photoelectrons once the wavelength hits that, okay? That right there is going to be related to your threshold frequency at which you start noticing the photoelectric effect occurring. Now, the threshold frequency is used to find your work function. Remember, the work function on a photoelectric surface is basically just the amount of energy it takes for this to even start, okay? Now, on your formula sheet, there is a formula for the work function. It says work is equal to h times your threshold frequency. Well, you know your threshold wavelength, so you could find your threshold frequency using that threshold wavelength. I'm going to build it all in one equation. This equation is not in your formula sheet, but remember, V equals F times lambda. V is, of course, the speed of light, so I can just call it C instead. So C is equal to F lambda. And then you can just divide it away to get F all by itself, and you can just throw that right into there. Bottom line is, I'm going to save you the trouble. It's work is equal to HC over your threshold wavelength. I'm going to call it lambda 0, right? So your threshold wavelength. Anyway, let's find this. So work is equal to, and just by the way, it'd be a really good idea to use H in joules. If you don't, of course, your answer is just going to be in electron volts, whatever, okay? 6.63 times 10 to the negative 34 times by C, which is 3.0 times 10 to the 8, divided by lambda 0, which is 832 times 10 to the negative 9. I got a work function of, let's see here, 2.3906 times 10 to the negative 19 joules. Okay, so that's the amount of energy needed to get electrons to come out of this. Now, where am I going with this? Your maximum kinetic energy, of course, really is just the energy of your emitted electrons. When they get emitted, of course, the higher your energy of your incoming light, the higher the kinetic energy of your emitted electrons. Don't get confused by the fact on your formula sheet it doesn't say EK for all of this, but what we do need to understand is that your energy, and I'll even just call it EK, or EK max, you could call it in this case, EK is going to equal HF minus your work function. This comes from the idea of conservation of energy, of course. The amount of work you have to put in to get this to start gets subtracted away from your kinetic energy in the end, okay? So that's that formula. It's not on your formula sheet. You do have to understand how that works, though. Instead of HF, I'm going to make a quick alteration here, of course, because the light we're really using is visible red light. We don't know the frequency of it. We can just change this so it's EK equals HC over lambda minus that work function. Well, HC over lambda, the lambda here is just your lambda for your visible red light. Might as well just throw that in. It's pretty much the same thing as what we did just to find the work function in the first place. I'm going to give myself some more room. EK is going to equal H, so 6.63 times 10 to the negative 34. Times by C, which is 3.0 times 10 to the 8, divided by lambda, which is 710 times 10 to the negative 9, and then minus that work function, put it in brackets over here, 2.3906 times 10 to the negative 19. Whew, all right, throw that in your calculator. I'll save you the trouble right now. It's going to be 4.11 times 10 to the negative 20 joules. That is the kinetic energy of the electrons that are going to be shot out of that photoelectric surface. Now, if you did this in electron volts, however, you are going to get a very different answer, and that's okay. Didn't say what units to put it in. If you used electron volts instead, you should have gotten 0.257 electron volts. And maybe that's a nicer looking number. You know, it's not crazy scientific notation, but whatever floats your boat. Generally speaking, kinetic energy, I'm more comfortable putting it in joules, right? It's a unit we're more familiar with, but again, electron volts are another way of measuring energy, and that is totally okay. All right, question 4. A photoelectric surface with a threshold frequency of that emits photoelectrons when illuminated with visible light. If the maximum speed of the kinetic or of the emitted electrons was 3.50 times 10 to the 5 meters per second, determine the stopping voltage. Ooh, all right. Pause the video here, give this one a try. All right, so this one actually isn't going to be too long, hopefully. There is a formula right on your formula sheet for stopping voltage. It's the only formula that has it built into it. Theoretically, there'd be alternative ways to find a voltage, but we're not actually going to need that in this one. The formula on your formula sheet that has this is EK max is equal to QV stop. Q, of course, is the charge of an electron, and V stop is our stopping voltage. Now, we don't know the kinetic energy, or the maximum kinetic energy of our electrons in this case. We know Q, right? So if we find this EK max, we're good to go. Now you might think, oh, EK max, we're gonna have to use that whole, big whole step thing from before, blah, blah, blah. Well, no, we actually aren't. This threshold frequency they give us, so F0, would be useful to find the work function of the photoelectric surface. But remember that EK max from the last question is HF minus the work function. In order to find that EK max using the whole idea of photoelectric surfaces, you would need to know your frequency or your wavelength of your visible light. And this question didn't tell us that. However, we can get around using this altogether because the question did give us the maximum speed of the emitted electrons. Why complicate things? Kinetic energy is something we would have learned back in physics 20. As a matter of fact, you probably learned it back in science 10. Kinetic energy, EK, is 1/2 mv squared. Electrons are still mass, they're still matter that have mass with them, right? So the old kinetic energy formula still applies. So if you know the mass, which we do, it's given to us always, it's on our formula sheet, and we know our velocity, which is actually given to us in the question, we don't have to mess around with this whole complicated idea of photoelectric surfaces. We can just use this formula right here. So EK max, I might as well just substitute that with 1/2 mv squared is equal to QV stop. Let's throw in the numbers that we know. Well, 1/2 mass is 9.11 times 10 to the negative 31. That's the mass of an electron. It is on your formula sheet. Times by the velocity squared, 3.50 times 10 to the 5 squared equals Q, the charge of an electron, which is also on your formula sheet, 1.60 times 10 to the negative 19 times by V stop. So we have everything except for V stop. In other words, we can solve for V stop. Just divide it over. V stop is going to equal, let's see, 0.349, and this, of course, its voltage is measured in volts. There we go. Good. So when it's asking for a stopping voltage, pretty much always you're going to be using this formula right here. Like theoretically, you can combine it with some of the old voltage formulas we had, but really there isn't much need to do that. Okay. Anyway, moving on. All right, this is going to be a two-part question. This is 5A. 5B is going to rely on the answer we have from this, so that's why I'm breaking it down into two pieces, so that if you don't get this question, you'll still be given the answer, and then of course you can solve the second half of the question. So pause the video. Actually, no, wait, I'll read it to you first. That would be a good idea. An X-ray photon with 40.0 kilo-electron volts, or kilo-electron volts, of energy collides with an electron, scattering it from its host atom, therefore ionizing the atom. This is why X-rays are so dangerous, or at least part of the reason why they're so dangerous. Of course, they can ionize atoms in your body, which can cause really bad things to happen. Anyway, the photon scatters at an angle of 60 degrees. Question A is saying, what is the wavelength of the scattered photon? Pause the video here, give it a try. Okay, so this is a Compton scattering question. There's only one formula that's dealt with this, and it's the one that says delta lambda, so change in your wavelength, is equal to h over mc times 1 minus cosine theta. Theta, of course, is the angle that the photon scatters at, which it gave it to us, right? So that's important to know. It's not talking about the electron here, it's talking about the photon. So we're good to go on that. We could find, the change in wavelength here. We have all this information, h, mc, h, of course, is the 6.63, blah, blah, blah. M is the mass of an electron that's given to us. C is the speed of light, of course. So it's all given to us. We're good. However, the question really is, we're looking for the wavelength of the scattered photon. So it's like we're looking for the final, wavelength. Delta lambda here really can be written as your final wavelength minus your initial wavelength equals h over mc, 1 minus cosine theta. Well, this is all well and good. We could find this, but we need to know our initial wavelength first. Well, we need to find that initial wavelength. The only other thing this question gave us was how much energy that photon had. Well, the good news is energy can connect to a wavelength. Remember, up on the top right-hand corner of your formula sheet, we see E is equal to hc over lambda. Well, the initial energy is this 40 kilo electron volts, right? We know H, we'll have to use the electron volt H to match the electron volts for the energy. C is just the speed of light, so we can solve for our initial wavelength, right? So I'll even just do it up here because I've already started up here. 40 kilo electron volts is 40,000 electron volts. This is going to equal H in electron volts, which we haven't used yet today, but it's a different number, a very different number, 4.14 times 10 to the negative 15. And then the speed of light is just the speed of light, 3.0 times 10 to the 8, all divided by lambda I. So if we want to find lambda I, your initial wavelength, just multiply it over and then divide by 40,000. Lambda I is therefore equal to 3.105 times 10 to the negative 11 meters. I'm going to put a box around this because this is going to be really, really, really important, not only for this question, but for the next question as well. So I'm going to put a box up so it's right up there and we know where it is. So we now know lambda I. Let's fill in all the information here because we can now find lambda F, right? So lambda F is what we're looking for, minus lambda I, which I'm going to put in brackets to keep it really safe, 3.105 times 10 to the negative 11. This is going to equal H. Now in this case, H, we should use it in joules because it's being matched with a mass as well as a speed of light here. We're not dealing with the energy in kilo electron volts anymore. So you know what, we will put this in the standard units. So 6.63 times 10 to the negative 34. There we go. Divided by mass, which is 9.11 times 10 to the negative 31, times by C, which is 3.0 times 10 to the 8. And then that whole thing, I'll even put big chunky brackets around it so we don't really lose it. We've got to multiply that by 1 minus cosine of our angle, so cosine 60, okay? What I did on my answer key that I've got in front of me here is I actually calculated this whole right-hand side first because this is going to be an absolute mess otherwise, right? So lambda F minus 3.105 times 10 to the negative 11 equals all of this multiplied together gave me, just find it on my page here, 1.21295 times 10 to the negative 12. And then, of course, to find your lambda F, we just have to add this thing over here. So lambda F is going to equal, and I'm not going to round it quite yet, it'll be important for the next question, 3.226 times 10 to the negative 11 meters. Ooh, too many ones there. 10 to the negative 11 meters. That I will put a box around, even though it's not my final answer, because again, it is going to be useful going forward, but we need to round to our nearest sig digs here. There's only going to be 2 sig digs because of this horrible 60 degrees. So lambda F is going to equal 3.2 times 10 to the negative 11 meters. That would be your final wavelength of that scattered outgoing X-ray photon. Good. Okay. That one was kind of sneaky because it gave you energy of the photon instead of giving you the wavelength and all that. So there was at least one extra step that you had to do there. But other than that, that's just a standard old Compton effect question. Okay. Now on to part B. We're going to need those 2 numbers. Okay. So part B, matter of fact, before we even start part B, because we're going to need those numbers so much and I want them so you don't have to make it inconvenient. Remember that lambda I is 3.105 times 10 to the negative 11. And lambda F, unrounded, do not ever use your rounded number when you're carrying it on. At least this isn't rounded as much as it could be. Like, I mean, there was an infinite real number of decimals there, but 3.226 times 10 to the negative 11. Hopefully you know what I mean, is that, you know, at least isn't rounded to like almost no sig digs, right? We want to keep as many sig digs as realistically possible here. Anyway, so those are the answers from before. We're going to need them. So just hang tight, okay? Anyway, an X-ray photon, blah, blah, I'm not gonna read that again. Assuming it was initially stationary, what is the speed of the electron using the conservation of momentum? So really we should be talking about the final speed of the momentum. Obviously, if it was initially stationary, the initial speed was 0, but what's the final speed of the electron using the idea of the conservation of momentum? This one's a very tough one. We never did one like this in one of the lessons, but I'm sure you can figure it out by using the formula in your formula sheet. Give it a pause, give it a try. We'll go over it in a second. All right, so we're going to go over this one now. Here we go. Let me just remind you, on your formula sheet, and in one of the videos, we did make like a little table talking about the momentum of things with mass versus things without mass. Photons don't have a rest mass. So in other words, we have to consider the momentum something a little different. Momentum for something with mass was P is equal to mv, but this doesn't have mass, so there's a different formula on your formula sheet. P is equal to h divided by lambda. Now, with the conservation of momentum, that just basically means the momentum before needs to equal the momentum after, okay? So what we could think of here, it's a couple different ways of doing this, but I'll show you the way I did this. I want to find how much my momentum is changing for my photon, okay? You could set this up a different way. You could set like the total momentum before equals the total momentum after. I'm just going to find how much my momentum is changing, so delta P, for my photon. Well, delta P is going to equal your final momentum minus your initial momentum, okay? If you want to set this up a different way, go for it. Like again, there's more than one way to get an answer here, but we're just looking for the final answer on this one. My change in momentum is my final momentum minus my initial momentum. And I'm just talking about my photon for now, okay? So delta P is therefore going to equal the final momentum, so h over lambda for the final. H, by the way, I'm going to use the standard 6.63 times 10 to the negative 34 over my final wavelength, which is 3.226 times 10 to the negative 11. Obviously, we didn't want to use the rounded number there because it would be losing a lot of information, minus the initial momentum, which again is h over lambda, so 6.63 times 10 to the negative 34, over the initial lambda, which is 3.105 times 10 to the negative 11. This gives me a change in momentum of negative 8.009 times 10 to the negative 25. Now this negative just means we're losing momentum on our X-ray. So that momentum has to go somewhere. This conservation of momentum, it's just one of our fundamental rules in physics. That momentum has to go somewhere, and obviously it's being transferred to your electron. Now if we think about this electron, since it had initially no velocity, that means its initial momentum would have had to have been 0. So all of this momentum is being passed on to the final momentum of the electron. The negative just indicates direction. We're losing it. That's why it's a negative. We're losing it on the photon, and we're gaining it on the electron. So the momentum of the electron is positive 8.009 times 10 to the negative 25. So I'll even write that down. 8.009 times 10 to the negative 25. That's my momentum of an electron. Electrons have mass, so we have to use that other formula. Mass is 9.11 times 10 to the negative 31. And velocity is what we're looking for, right? We're looking for the speed of the electron. So we just need to divide that 9.11 times 10 to the negative 31 over. My velocity is therefore equal to 3 sig digs here. Well, actually, we don't even need 3 sig digs. It really could be 2 sig digs. I don't know how many sig digs we're going to use here. Technically, we used a 60 way earlier on. I'm just going to say 3 just because whatever, who cares? 8.79 times 10 to the 5 meters per second. Hopefully you were able to get that. Again, conservation of momentum is the strategy you had to use in this question because it asked another viable way of doing it, although it would have given you a different answer as if you had looked at it from a conservation of energy approach, okay? It probably would have given you a different answer anyway. I never actually tried it, but still there's different ways of going about this for different purposes. All right, we're done. That was a longer lesson today. I apologize. But for practice, any remaining practice problems in your EMR Part 1 or Part 2 booklet, just as I asked yesterday, your unit exam on Thursday, which is tomorrow, we'll cover both halves of the unit. It's entirely written response. Again, if you need any help, if anything today was still confusing, please reach out to me and I'll give you some help. Best of luck.